Hi, I want to talk about the concept of entropy. Now, entropy, as it was first sort of worked out and used, can be thought of as a macroscopic state of a system, similar to temperature or internal energy. So you may have heard folks refer to the temperature or the internal energy as state functions or state variables. Entropy is also a state function or a state variable. And in physics, one of the ways that we can define the thermodynamic temperature is the derivative of the heat with respect to the entropy of a process. Often you would think about this as the reverse. 1 over the temperature would be the derivative of entropy with respect to heat. But what that leads us to is a general expression for how we could calculate the macroscopic entropy. Our change in entropy over some infinitesimal amount of heat dq is equal to dq divided by the temperature at which we have transferred that heat. Now, there's also a microscopic, in a way, and I've written microstatic semi-ironically over here, of calculating entropy, because if we take a look at mechanics and thermodynamics as a series of statistical processes, there's a more powerful way of defining entropy. And entropy in that framework is based off the number of microstates for a given macrostate. So to explain this microstatic picture, I want to talk about how poker hands could tie into this idea of entropy. So in terms of microstates, the entropy would be equal to Boltzmann's constant 1.38 times 10 to the negative 23 joules per Kelvin times the natural log of the number of microstates for any given macrostate. Now, these aren't thermodynamics. I know a lot of thermodynamicists that do play a lot of poker, though, so the two go a little hand in hand. But the best hand in poker to have is the royal flush. And the reason why it's the best is it's the lowest entropy hand. There are only 4 possible ways that you can have a royal flush: having the 10, jack, queen, king, and ace of any of the 4 card suits: clubs, spades, diamonds, or hearts. Now, if you just wanted to figure out, if you deal 5 cards, how many poker hands you can get, well, the total possible number of poker hands is 2,598,960. So 4 out of 2.6 million is a pretty small percentage. Now, if you wanted to think about it in terms of thermodynamic entropy, I could take the natural log of 4 multiplied by 1.38, so in units of 10 to the negative 23 joules per Kelvin, we'd have an entropy of 1.91. The smaller the entropy, the fewer the number of unique ways of expressing that quantity, and the smallest amount of entropy, if we had only one state, we would get the natural log of 1, which means there would be 0 entropy for a state that could only exist once in a given macrostate. So other macrostates in poker: straight flush, 4 of a kind, full house, flush, straight, 3 of a kind, 2 pair, 1 pair, and just having a high card, but not having any of the other pieces. So each one of those ranks are based off of the relative rarity of that macrostate. So in terms of microstates, there are 36 ways to have a straight flush that isn't a royal flush. There are 624 ways of having 4 of a kind. There are 3,744 ways of having a full house. There are 5,108 ways of having a flush. Straight, 3 of a kind, 2 pair, 1 pair, just having a high card. All of those have increasingly more microstates within that given macrostate. So you can think of these less useful hands in poker as being higher entropy hands. So a royal flush, if it has an entropy of 1.9, a straight flush has an entropy of 4.95, just about 5. Four of a kind has an entropy of 8.88. Full house, 11.4. Flush, 11.8. Similar in terms of usefulness, full house is slightly more useful. All the way down to just having a high card, which would have a thermodynamic entropy, if it were a thermodynamic system, of 19.4. So, in information theory, the concept of entropy is used as a way of evaluating usefulness of information. There are a lot of applications and fields that are starting to apply these statistical principles that we've used in thermal physics to other sorts of systems to try and gain different and more powerful understandings of those systems. Now, we're going to, in this class, just focus on macroscopic looks at entropy, working with the macroscopic thermodynamic variables, temperature, pressure, and volume. So there are a couple of special cases that are pretty easy to talk about with entropy. The first is if you have an adiabat. For an adiabatic process, there's no heat transfer. So if there's no heat transfer, the integral of 0 is a constant, so our change in entropy would be 0 under an adiabatic process. Whatever entropy there is in that process, that entropy remains the same. Now for melting, boiling, freezing, or condensing, those processes involve heat, but they involve exchanging heat at a constant temperature. So for phase transitions, there is an entropy of transition. Now the energy of transition, the heat that we need, is equal to the amount of material we have times the latent heat of that transmission. So if it's melting or freezing, it's the heat of fusion. It would be a positive heat for melting, a negative heat for freezing. For boiling or condensing, it would be the heat of vaporization, positive heat for boiling, negative heat for condensing, and our change in entropy for those processes would be equal to our heat, the amount of material, times the latent heat, divided by the temperature of that phase transition. Thanks for watching.